this way. I guess you curl the fingers up.
Fingers in the direction of velocity, and then you want that to curl into the direction of the magnetic field.
Oh, you would go like this, okay.
So don't give up yet, Devon. Enrique?
See, I thought the negative Q would flip it to the other side.
That. You saw it last time and you missed it this time. Yeah, it is, the electron is gonna be moved that way because that Q there flips it.
Because it's positive, because it's negative.
So an electron would also be moved over here. Fortunately. Because now, if it's positive charge flow, this will be the higher potential, this will be the lower potential. If it's the negative charge is flowing, this will be the low potential, this will be the high potential. So now we can then stick a galvanometer or a voltmeter or whatever you happen to have, something very sensitive because it's not like it's a huge difference. And you can now measure which is the higher potential side and which is the lower potential side. And this is the point where we realize it's negative charge flow creating current. This is known as the Hall effect. And hoping to pinpoint an actual date for it. Apparently not. It was in the 1800s, I know that part. Yeah. Oh, there we go. I just don't have the date written down. I was thinking the 1880s. Other than Benjamin, in terms of American science, Ben Franklin was obviously a very key player. And then there's basically a drought of notable US physicists, even though they weren't called physicists at the time, physicists until you get to 1890s. About a 140-year period. But Ben Franklin made his mark still in the colonial days. So I guess you question whether it was really, he was an American at that point, I'm not quite sure. I was on a trivia quiz, I was doing a trivia quiz once, and they asked, the question was, in what country was George Washington born? I wasn't sure how to answer that. The official answer, we got it marked wrong, because the official answer was he was born in the US, and even my daughter, who was like 5 years old at the time, said, the United States didn't exist then.
No.
Sorry, holding a bridge still.
No, I'm good.
Was that?
I was just agreeing with you.
Okay, yeah.
That's funny.
Thank you for agreeing with me. All right, so we have the Hall effect now. We can do the, we now know it's negative charges flowing. And at that point, they're going, we're not changing the convention, current's still flowing the way we said it's flowing, and we're not worried about anything else, just the electrons going the other way. Questions before we extend this formula to deal with current? Now there's a fancier derivation of what I'm about to do. I'm just gonna stick with a simpler one. It still gets you to the same place. So this Q here is the charge that's zipping by. So if I got a whole bunch of charges flowing by, then we call it a current usually. So that's going to be equal to Q dx dt, or d whatever letter you're using, dt cross v. So I'm dealing with some particular amount of charge passing by in a particular amount of time. I'm just going to move the dt over, so I'm left with Q over dt times dx cross v. probably should somehow differentiate between my X and my cross. That's an X, that's a cross. And this charge over time is just by current. Now typically they don't use X, so typically they just use L. Probably should have started with that earlier, but the LDV. I guess technically that's the differential of the force, or force, is I, L cross V. I know if they fast and loose with the formality of it, so if you're good with this, fair to what I just did. The direction of L is the direction of the current flow. So this could equally write it as IL V hat cross V, where this is the direction of the current flow, of the positive charge flow, even though we know it's negative charge is moving almost all the time. It's still the direction of the charge flow, or current. The direction of L equals direction of current. So this equation right here, this IL cross B, is the force on a current carrying wire. So if I have a magnetic field here, coming out of the board, and I have a wire running through it, and let's just make the current flow up this time, which way will the wire be forced?
Right.
How are you doing that? So the direction of the current flow, direction of L, magnetic field's going that way. This wire will be forced in that direction. So if I have two wires with the current flowing in the same direction, we'll call this I1 and I2. The current is creating a magnetic field that the other wire is going to experience. So I1 will create a magnetic field that I2 experiences. I2 will create a magnetic field that I1 experiences. And so they will react to each other. So the question is, which way will the wires be forced? So let's do it step by step, unless somebody want to take a shot at it first.
I mean, I feel like then that effect is gonna be zero, just because the wires in the room aren't moving, and a lot of them are, bound together, but beyond that, I don't.
My first thought was the magnetic force that they experience is, up here is not huge.
Yeah.
And especially if you have alternating current, you've got current flipping back and forth like that. So at 60 times a second, so any force, even if they're oscillating, you wouldn't necessarily notice it.
Yeah.
Could they go like in different directions, or do they move like together?
Oh, it would be cool, but probably very dangerous if they moved in the same direction.
Okay.
The net result is going to be zero in the fact that whatever force I2 exerts on I1 has to be equal, but in opposite direction to that I1 exerts on I2. If you can set it up that the current that they would move together, then you violated Newton's third law. And we don't want to do that. Not in this class, young man. So, if they're gonna move in opposite directions, that means they either go out or they come in. Let's take it step by step then. Alright, so I1, we'll make this one blue. What is the direction of the magnetic field here created by I1?
Out of the board?
Yep. So thumb's the direction of current, magnetic field is going into the board here, out of the board, out here. So into the board, out of the board. We'll make the other one red. What is the direction of the magnetic field here at I1 because of the current I2?
It's gotta be out. You said that one was in.
The magnetic field, that's not the direction of the force, that's the direction of the magnetic field. But you're saying the magnetic field would be out here?
Mm-hmm.
How'd you get that?
Guessing it'd be, I'll be honest, I guess it's the opposite.
Ah.
Yeah.
Yeah, the opposite doesn't work here with the magnetic fields.
Mm-hmm.
You have to go back to the right-hand rule. That thumb in the direction of the magnetic field. So it's going in over here, out over here. So I1 is a current that's flowing down, the magnetic field is coming out. Which way will I1 be forced?
To the right and to I2?
You said to the right?
Yeah, we did.
That, okay, this way.
Yeah.
If we did L cross B, L cross, see, magnetic field was going out. So L cross B should be in. What am I missing here? Or do wrong? Right, so magnetic field is going, oh. You said in, I think I contradicted you and I can't remember. Into the board, out of the board, that is correct. I drew my symbols wrong. Into the board was X's, so those would be X's. Out of the board would be dots. So not opposite, okay. So L cross B points it that way. L, the direction of the current flow, B is going into the board, thumb points in. Now from Newton's third law, we know that I2 better be going that way, but let's just confirm it.
How do we know which way to orientate our hand? This way or this way?
You want your fingers to bend towards the second one the simplest way. So if L is going that way, I got 360 degrees of orientation here I could go with. But since B is going this way, I want my fingers to bend so that they would point
Gotcha.
in that direction.
Gotcha. I just got confused. And I was like, oh, this way. No, this way.
I am happy to say I haven't seen anyone do the left-hand rule yet. So thank you. All right, so now we have current flowing this way, magnetic field's going out. It's gonna be forced that way as expected. Newton's third law is satisfied. The universe stays in balance. And so now, we're about to take a break here because I need time to set up. I have a current flowing through some strip here. So the current here is flowing down, the current here is flowing up. Which way will these two sides be forced?
Towards each other? No.
It's either towards each other or away from each other. So,
I wanna say away. You said away. Feel like it's away. I
I hope so, since if they're going in the same direction it's towards, if I flip one of them, something better be opposite. They should move that way. Let's take a break here. I'll set up, and we'll actually see this.
I had a question.
None of you are in frame right now. All right, so the first time I did this demonstration, I had about 15 AA batteries, which I had lined up, and it worked, although there was, if any of the batteries are just slightly off, it'll spark and drain the batteries quickly, and it just doesn't work particularly well. But you have to get the batteries and get them all pressed together, so I used a lot of tape, and it worked, and I thought, oh, excellent. So then I tried with the power supply when I came up here, and it worked beautifully. Next several years, it twitched a little bit. The demonstration was just absolutely horrible. And then I was in the class, and it didn't work, and I thought, why if I just turn it around? Instead of the shiny side in, do the dull side, or whichever way I flipped it, and it worked beautifully. Now, dull side, shiny side, it's a matter of to my knowledge, there's no difference between them from an electrical point of view. However, it seemed to do the trick, and it's actually tends to have worked rather well with it recently. So, knock on wood, here's hoping it works again. So what's gonna happen, crank that up, is when I turn it on, the plus side is this side over here, so the current's gonna flow down this side and then come up the other side. So for this region in the middle, current's going in opposite directions. And so the prediction is that they should come out. Because there's so little resistance here, it's gonna quickly trip the fuse, or the circuit breaker, not the fuse. Circuit breaker's gonna flip, and it should, basically we're gonna lose all current very quickly. You should hear a click, easy enough to reset. Work. There we go. As predicted. And all I'm doing is just resetting it, and it immediately trips the breaker. It no longer wants to. There we go. To me, that's just so cool that it actually works. So you need to have something light enough that it will actually move under the force, because it's not a whole lot of force here. You want something that is close enough together, so aluminum works nicely that I can get it close. If I touched it up here, then basically it short circuits it, the current's gonna come here, then jump across wherever it's touching, and then come down the other side, and the rest of it, nothing should happen. And there's a lab where we do this, which is probably my favorite lab, and the results are hit or miss. But it's just the fact that you then can do measurements about how far it does spread apart, and then make prediction, and then compare that to what would have been predicted based upon the resistance that of the aluminum foil and the voltage that potentially you're getting to as you do this. So anyway.
What would happen if you can continue to hold voltage to it? Would they just find a spot of equilibrium?
Yeah.
Okay.
Because they're also pulling, the natural tendency is to hang like this. And so you've got
Gravity and mass.
gravity as well as the natural stiffness of aluminum. And in the predictions in the lab, and that is one thing I deprive the students of, is in the lab, I basically gone through those calculations already and presented the formula. Now, if you wish to recalculate the formula, and that. And I tried one other thing. When it was not working well, I tried something else. I want to see if this will work. I think this will be too heavy. But to get closer to them, even with each other, I can get it closer. Let's find out what happens. Oh. Still works.
It's a hold it down sound more.
Yeah.
Yeah.
So again, if you want to, oops, before I start, let's get the current turned off. And I don't want too sharp an edge at the bottom, but also at the same time, I don't know if that's touching there. Last time, I think. Go. I think that worked rather nicely. Anyway. In physics demonstration, that worked. Woo! Golf clap. Now I do this probably, once a year. You can see the remnants of the previous one that I used. Hopefully this will be around long enough for me to reuse it. And I did film it. Yay. So let's take a look at an oversimplified version of the formula that is the force acting on these. We have this formula for the force on one of the wires, or for a wire in a magnetic field. We have a separate formula for the magnetic field created by a wire. So I'm going to combine those two. So sort of recapping that bit. The magnetic field that is coming from a wire was mu naught I over 2 pi r. We derived it from V sub r, but it can also be derived from Ampere's law. Matter of fact, we use this to pseudo